Welcome to this video. Part of your homework tonight is learning how to solve problems like numbers 8, 9, 10, and 11. These are so important, you will see them on every future test that we take this semester. So take note. Okay, in these problems we have this first one is dealing with kinetic energy, so let me write the generic formula, 1/2 mv squared. And in problem A we have two balls, ball A and ball B. All right. What do we know? Ball A has a mass m and a speed v. So as soon as I write those down under the A column, no longer is m a generic variable. M now stands for A's mass, and likewise for v, that's A's speed. It would be wrong for me to say that B has a mass m, because B's mass is not the same. Okay, let's read ahead. Ball B has 2 times the mass of A, so 2 times A's mass, and 1/3 the speed of A, so 1/3 of A's speed. That's a 3. 1/3 times V. Ball A has a kinetic energy of 27 joules. Calculate B's kinetic energy. Ke of B equals question mark. That's our unknown. If I write the formula for kinetic energy twice, once for A, once for B, the formula is kinetic energy equals 1/2 mass times speed squared. And I'll do that again for ball B. Kinetic energy equals 1/2 mass times speed squared. I have 2 equations, so I will probably have to substitute one into the other, right? Usually when you have 2 equations, you combine them, and substitution is how we combine equations. Let's plug in. The kinetic energy of A is 27 joules. The mass of A is m, and the speed of A is just v. How about for the other ball? We don't know its kinetic energy, so we just put the variable. The mass is 2m, and the speed is 1/3 times v. Don't forget to distribute the square to everything in parentheses. That turns into 1/9. If I rewrite the right side of the equation for ball B, I have 1/2 times 2, don't simplify, times m times 1/9 times speed squared. So why did I tell you not to cancel out the 1/2 and the 2? Because we have to substitute. If you take away 1/2, take away m, and take away v squared, you can replace those 3 things with an equal quantity. What is equal to 1/2 times m times speed squared? 27 is equal to those 3 things. So I'm going to replace 1/2, replace the m, replace the v squared. All of those 3 things go away, and in their place I have 27 joules. What did I not replace? What is remaining in the equation? Well, the 2 didn't go away. I didn't substitute for that. The 1/9 didn't go away. So when you calculate 2/9 of 27, 27 over 9, that's 3. 3 doubled is 6 joules. The answer is B. Although it should have 3 sig figs, shouldn't it? Whoops. That's how you solve this problem. The final step is substituting. This is what most people mess up. Most people forget to include the 1/2, right? And they instead, what they'll do is they'll cancel these out, and then they'll substitute for mv squared, and they'll say that mv squared is 27, but it's not 27. mv squared times 1/2 is equal to 27. That's why you keep the 1/2 there. Okay, number 9. Good. We'll do this one a little quicker. Instead of making a chart, I'm just going to write down the equation. Kinetic energy is 1/2 mass speed squared. Kinetic energy is 1/2 mass times speed squared. All right, ball A has a mass m, a speed v, that goes here. They are calling its kinetic energy Ke. All right, easy enough. Ball B has 3 times the mass. Okay, so B, for its mass, let's see, 1/2 mass speed squared. So this is mass. Okay, so for B, I put in, what was it? 3 times the mass of A. So 3 multiplied by A's mass. And it has 1/4 the speed. Okay, so 1/4 multiplied by A's speed. B's kinetic energy equals, well, it would be wrong to put Ke here because it's not the same amount as this. If you put the same exact Ke here and here, you state that they are equal, and they're not. How do I fix this? You simply come up with a new variable, Ke2 or Ke subscript b. I'll do Ke sub b as my new variable. Okay, so I'm trying to solve this. What is B's kinetic energy? That's my unknown. All right, well, the first thing I do is distribute the squaring to everything in parentheses. Don't simplify anything. I have 1/2 times 3 times m times 1/4 squared times speed squared. Very good. What's my final step? Substitute. In place of 1/2 m and v squared, I'm going to put the original kinetic energy of ball A. Here's another way you can think about that. We're allowed to multiply and divide in any order. So let me multiply these 3 things first, and then next I'll multiply by 3 times 1/16. Right? So all the things here are the same as what's here. I'm just changing the order, and that's something I'm allowed to do. And then my final step, as I said before, is substituting. So the 1/2 mv squared is equal to, well, that's the original mass of A and the original speed. So this is all equal to A's kinetic energy, which we called simply Ke. So I can substitute and say B's kinetic energy is the original Ke multiplied by 3/16. And which answer is that? It's choice C. Isn't there some joke where every multiple choice question, if you don't know, just guess C? Well, worked out that time. 10, we're gonna go quicker now. I look at this, I say potential energy, spring constant, compression. I know which equation we're using. The equation for elastic potential energy. 1/2 times the spring constant times the compression squared. And let me guess, are there going to be 2 springs? Yeah, probably. Spring A, spring B? Nope. Spring 1, spring 2. All right, I'm not fooled. Spring 1, spring 2. All right, so the equation is potential energy equals 1/2 times the spring constant times the displacement squared. Potential energy equals 1/2 times the spring constant times the displacement squared. All right, what'd they tell us? The first spring has a constant K, a potential energy PE, and that's when it's compressed 10 centimeters. Should I convert that to meters? It doesn't hurt. Okay, 0.1 meters. Determine the potential energy in a second spring with twice the spring constant, so 2K, and 1/3 the compression. Instead of calculating the value, I'm going to be clever. I'm going to call this X, and I'll call this 1/3 X. Right, the numbers don't actually matter because I'm just going to substitute at the end, so this is a better way to do it. Haha, I'm being tricky, I'm being crafty here. I'm not going to give the value that they showed here. I'm just going to put in x and 1/3 x. What do I put right there? PE? No, that would be wrong. The energy isn't the same as this PE. So let me make a new variable PE for spring 2. All right, next I make sure to not forget, distribute the square to everything inside. 1/3 squared is 1/9. And PE2 equals 1/2 times 2. I'm not going to simplify. I don't fall for that trap. Times k, there's the k, times a 9th, right? 1/3 squared, times x squared. Then I take the 1/2, I take the k, I take the x squared. Why am I taking those? Because I can substitute for them. 1/2 times k times x squared. Whoops, k, there's the x squared. Those three things together, 1/2 k x squared, together they are equal to the original potential energy. And my first equation states this clearly. So in their place, I'm going to put the original potential energy. And then I'll combine the stuff that's left over, the stuff that didn't get substituted in for. And this is my answer. The new potential energy is 2/9 of the old. Number 11, final question. Oops. 2/9 times the original PE. Okay, a first spring has 36 joules of potential energy when compressed X. How much potential energy does the same spring possess? That's a trick. If it's the same spring, it is just as stiff. It has the same spring constant, right? Which, remember, spring constant stands for the stiffness. If it's the same spring, that has not changed. However, it's compressed just half the distance. That's 1/2 times x. All right, scenario 1, scenario 2. Potential energy is 1/2 times the spring constant times x squared, and I'm using k and x, but instead of PE, I should use the value they gave me, 36 joules. In the second case, I don't know the new potential energy, so I don't plug in for it. I come up with a new variable. I do know the spring constant. It's the same k as before. And I know that the compression is now 1/2 of the original compression. Distribute the square to both things in parentheses. That's a common mistake. And what do you get? There's a 1/2. There's a k. There's 1/4 because I squared it. And an x squared. Finally, we substitute. I'm using the top equation to substitute. So in order to plug in 36 joules, I need to find 1/2 and take it away. I need to find k, I need to find x squared and take those away. Here's my 1/2, here's the k, here's the x squared. Collectively, they equal 36 joules. So I substitute for those things. And now I have 1/4 times 36 joules. And what does this equal? I'll just go to the next line. Whoops. What does this equal? 9 joules. And that's how you solve these problems.